We are going to start a very important chapter from application of derivative, that is maxima and minima. Maxima, it is the plural form of maximum, and minima is the plural form of minimum. Okay, you see a function y is equal to f of x. It is defined from closed interval a b. Okay, that means from the point a the function is defined. This is the graph of this function to b. Okay, so from the graph we can see, at first understand this graph. At first from a the graph is increasing, after that it is decreasing. So at this point p it has the maximum, then again it is decreasing, and suppose this is the point q, then here it is the minimum, again it is increasing, then decreasing. So at the point, if this point is r, again maximum, again minimum. Okay, so what is local maximum and what is absolute maximum? At first, local maximum. The function y is equal to f of x has its maximum value at the point p if, again I am telling, at the point p the function attains its local maximum value if f of p, that is the functional value at the point p, it is greater than f of x, where x belongs to open interval p minus delta to p plus delta, where delta is a very small value greater than 0. This interval, it is known as neighborhood of the point p. Again I am telling, for all values, for all points at the neighborhood of p, if f of p is greater than the functional values at all the points in the neighborhood of p, then we can say that at the point p the function f of x has its maximum value. You see, I just given this interval, it is very small interval, whatever you may take, it is smaller than it. In this neighborhood, you see, at all the points the functional values, if we draw the lines, the length of the lines are at the functional values at that particular point. You should see the length of f of p will be maximum than other functional values. That's why at the point p the function attains its local maximum value. Okay, that means as f of p is maximum, so f of p plus h minus f of p, it will be less than 0. Maximum value is subtracted. Similarly, f of p minus h minus f of p, it is also less than 0 for a small value of h which is greater than 0. That means f of p, the functional value at the point p, it is more than the functional value at the left hand point or at the right hand point of p. Okay, now you see, at the point p maximum value attains, at the point r again maximum value. You see, at the point b, if you take the neighborhood of b, you see, at the point b there is no right hand side, but left hand there exists. So in the neighborhood of b, the points, we have to take the points only which located at the left hand side of b. In all those points, f of b is the maximum. For all those points in the neighborhood of b, f of b is maximum. So f of b is also a local maximum value. Okay, now in these, which are the f of p is a one local maximum, f of r is one, and f of b another. Among these, f of p, f of r and f of b, which length is the most? F of r is the most. That's why in this whole interval f of r is most, that's why this point, at the point r, the function y is equal to fx attains its absolute maximum. Okay. Similarly, y equal to f of x, the function y equal to f of x attains its minimum value at the points you see. Again, if we take this point A, at the neighborhood of A, you see in the neighborhood of A there exists no left hand side, only the right hand side. Okay. In this neighborhood of A, all the functional values are greater than f of A. If we draw some lines here, you see all the lines are greater than f of A. Okay. That's why f of A is smaller or smallest among all the lines or all the functional values at the neighborhood of A. That's why f of A is the minimum value here, locally minimum. Again, at the point Q, if we take neighborhood of Q, that means if we take some points in the left hand and right hand of Q, suppose this is the interval which is denoting the neighborhood of the point Q. In all the points f of Q, the functional value at the point Q is the smallest among all the other points in the neighborhood of Q. That's why f of Q is locally minimum here. And again at the point S, you see the same things happen. That means the function decreasing, you get the value, then again it is increasing. Not at the extreme points, mind it. Okay. Here also you see the function is decreasing, then again it is increasing. Then what is the definition for local minimum? The function y is equal to f of x has its minimum value at q in closed interval ab if f of q is less than f of x, where for all x belongs to, that means for all the points in the neighborhood of q, that is the interval neighborhood of q, that is the interval q minus delta to q plus delta, where delta is a very small value greater than 0. As q is, f of q is the smallest, that's why f of q plus h minus f of q, it is the smallest among all, so it is greater than 0. A large value minus a small value, that is greater than 0. Similarly, f of q minus h minus f of q, it is also greater than 0, where h is a small value which is greater than 0. Therefore, f of q is local minimum at q comma 0 at the point q. So what is the local minimum value of the function? At the point q, the local minimum exists, very good, but what is the value? What is the local minimum value? That is the functional value at that particular point, that is f of q. Okay. Now among all such minimum values, that is f of a, f of q, f of s, f of q is the smallest. That's why it is the absolute minimum. Absolute minimum means in this interval, for all functional values, which is the smallest value of the function, that is f of q. That's why f of q is known as absolute minimum value, which occurs at the point q. Now if we discuss about the graph of this function, you see at first the graph is increasing, then decrease. Okay. So you see increasing, then decreasing. So in between these two portions, from the point A to P, the graph is increasing, then P to Q, the graph is decreasing. I wrote here I for increasing and D for decreasing. So in between these two portions, the point P, at the point P, the graph attains its maximum value. At first it is increasing, by increasing it attains its maximum value, then it decreased. Okay, after that it is decreasing, then increasing. So by decreasing it attains its minimum value, again it is increasing, then decreasing. So whenever the graph is at first increasing then decreasing, then it will attain its maximum value, and if the graph is decreasing then increasing, then it will attain its minimum value. You see. So at these points where the graph attains its maximum or minimum value, at those points the first order derivative f dash x is equal to 0. The points where the f dash x is equal to 0, these points are known as critical points. Okay, the point where the graph attains the function attains its maximum or minimum value, those points are known as critical point. That means the point where the first order derivative is equal to 0. Okay, now you see in this portion from a to p it is increasing, that means the first order derivative greater than 0, and from p to q it is decreasing, first order derivative f dash x less than 0. Already we learned in increasing decreasing chapter. So in this portion f dash x greater than 0 and this portion f dash x less than 0. Ultimately f dash x it is decreasing, the values of f dash x is decreasing, from positivity it got its negativity, that means the values are decreasing, by decrease it got its negativity. As f dash x it is a decreasing sequence, that means again if we do the derivative of it, it will be less than 0 for decreasing function, that means f double dash x less than 0. So at this particular point where maximum value attains by the function, at that point the first order derivative is equal to 0 but the second order derivative less than 0. That means at the point where the function attains its maximum value, at that point first order derivative f dash x is equal to 0 but second order derivative f double dash x it is less than 0. Similarly you see from p to q the function is decreasing, then q to r it is increasing. So ultimately at first you see f dash x less than 0, then this portion f dash x greater than 0. From negativity it becomes positive, that means in this portion from p to r f dash x is increasing. If f dash x is not increasing, then how it will become positive in this portion q to r. Okay, so ultimately f dash x increasing, that means if we again do the derivative of this f dash x, it will be positive. So f double dash x greater than 0. So at this particular point q you see when minimum value occur, then the first order derivative is equal to 0, as it is also a critical point. First order derivative is equal to 0 but second order derivative it is greater than 0. Okay, and you see between any to maximum value there exists a minimum value. Similarly between any to minimum there exists at least one maximum value of the function. Okay, you see in the previous graph the function is increasing then decreasing, again increasing then decreasing, that is alternatively. In some cases it is increasing, then in the next interval again it is decreasing, again in portion of the interval it is increasing. Okay, alternatively. But here you see in this graph decreasing then again decreasing, and at this point the first order derivative also equal to 0 but there exists no such maximum or minimum value. That's why this point is known as saddle point. Now a problem, we have to find the maximum and minimum values without using derivatives. Okay. Now the first one, it is given f of x is equal to 4x square minus 4x plus 4 on the set of real numbers. So this is the given function. Making it in square form, this can be written as 4 into x minus 1 by 2 whole square plus 3. Now this x minus 1 by 2 whole square, it is always greater than equal to 0. So multiplying 4 both side, 4 into x minus 1 by 2 whole square greater than equal to 0. Now adding 3 both side, we will get this expression greater than equal to 3. That means, what is this? This is the function f of x which is greater than equal to 3. That means the minimum value is 3, but there is no upper bound, that is there is no maximum value. Similarly, in the second case, there is the in the second problem, given f of x is equal to minus of x minus 1 whole square plus 2. Okay, this x minus 1 whole square is always greater than equal to 0. So minus of x minus 1 whole square less than equal to 0. Adding 2 both side, this expression less equal to 2, that is f of x less than equal to 2. So the maximum value is 2, but the minimum value does not exist. Next problem is find the local maximum or local minima using first order derivative test. Also find the local maximum or local minimum values. The function is given f of x is equal to x cube minus 3x, then differentiating we will get f dash x is equal to 3 into x square minus 1. Now if f dash x is equal to 0, it gives x is equal to plus 1 or x is equal to minus 1. That means these 2 points divides the total number line in 3 halves, minus infinite to minus 1, minus 1 to 1, then 1 to infinite. Now in this portion minus infinite to minus 1, f dash x, it is greater than 0. So f of x is increasing, and in the second portion f dash x less than 0, that is f of x, it is decreasing, and in this third portion, that is x greater than 1, in this case f dash x again greater than 0, that is fx is increasing. So you see, in this portion it is increasing, in this portion it is decreasing. So at the point minus 1, f of x has its local maximum value. What is that value? We have to put minus 1 in place of x in f of x to get the maximum value, and in this portion it is decreasing then increasing. At first decreased then increased. That means at the point 1, the function f of x has its minimum value. So to get the, what is the minimum value? To get the minimum value, we have to put 1 instead of x at f of x. So the maximum value is 2 and the minimum value will be minus 2. Another problem, find the local maximum or local minimum. Also find the local maximum values, local maximum or local minimum values. This is the most important process in this chapter. That is, this is the given function f of x is equal to x into e to the power x, differentiating both sides. So first order derivative f dash x is equal to this one. Now if f dash x is equal to 0, then this expression equal to 0, either e to the power x is equal to 0, from that we will get x is equal to minus undefined, minus infinite, and x plus 1 equal to 0. From this we will get x is equal to minus 1. Again, if we differentiate this f dash x, we will get the second order derivative of fx, that is f double dash x is equal to this one. Now we have to check the value of this double derivative for x is equal to minus 1. For x is equal to minus 1, it is greater than 0. That means fx has its minimum value at x is equal to minus 1. Then what is that minimum value? Putting x is equal to minus 1 in this given function, we will get the minimum value, and here there is no maximum value, only it has the minimum value. Another problem is given. We are to find the absolute maximum or absolute minimum values in the given interval. The function is given f of x is equal to cos square x plus sin x, and the interval is given close interval 0 to pi. So given f of x is equal to cos square x plus sin x, differentiating both sides with respect to x, first order derivative is equal to this. If first order derivative is equal to 0, from that we will get x is equal to pi by 2 or x is equal to pi by 6 or pi by 6 in the interval close interval 0 to pi. Now we have to check the value of the second order derivative in these points. So again differentiating f dash x, we will get f double dash x is equal to this one. Now the second order derivative at the point pi by 2, we got it is 1, that is greater than 0, positive. So if second order derivative is greater than 0, that means at that point the local minimum value exists, and that is f of pi by 2 is equal to 1. And at x is equal to pi by 6, we got f double dash pi by 6, that is equal to less than 0. So local maximum value exists and it is equal to 5 by 4, that is putting this pi by 6 in the given equation which is given for f of x. Okay, we got f of pi by 6 is equal to 5 by 4, and similarly the second order derivative for the point 5 pi by 6, we got again it is less than 0, and so local maximum value exists at the point 5 pi by 6 and it is also 5 pi by 4. Now to find the local maximum or local minimum value, to find the absolute max and absolute min value, we have to find the functional value at the end points also, that is at the point 0 and at the point pi, both are equal to 1. Okay, so among all these values we got, which one is minimum? 1. So the absolute minimum value is 1, and which is maximum? 5 by 4. So the absolute maximum value is 5 by 4.